Welcome everybody to the snack program offered by Rotary Club each Thursday, obviously at noon. The snack is different from our Tuesday program in that there's a little less to it. You'll find it to be a little less formal than the Tuesday programs. There's no pledge, no invocation, or club business. The program will last about an hour. Of course, you can still count on high quality programming and content because we do have 2 Marquette students talking to us today. Typically, we feature a member of Rotary or a Rotary-connected organization with ideas pertinent to how we are living today. Today, we welcome 2 engineering students, Claire Randall and Matt Frank, who are both Marquette engineers. Claire is a civil engineer from Marquette. Matt is a construction engineer studying at Marquette. They're both seniors. They will talk about their work on pedestrian bridges in Guatemala as part of the Engineers Without Borders chapter at Marquette University. Next week, we will welcome Rotarians at 5 p.m. for the Thursday happy hour. Please submit your questions via the chat. I'll be monitoring that. I'm Mark Federle, by the way. I should have said that. And no, I'm not driving. I am writing. So as my face bounces around, that's what's going on. I'll keep an eye out on the chat questions and share them with Claire and Matt when the right time hits. And now it's my pleasure to introduce Claire Randall and Matt Frank.
Hello, everyone. Good morning. We'll just go ahead and share our screen.
All righty. We're just getting our PowerPoint open, and here we go.
All righty. Yeah, so like Dr. Federle said, my name is Claire. This is Matt. And yeah, we are the project leads for the Las Guacamayas Pedestrian Bridge project, which is what we will be talking about today. So quickly, I'll just click through all these. We'll just do a quick overview of kind of how the project process works with EWB. So I'll just read the mission real quick. So EWB USA is a nonprofit humanitarian organization established to support community-driven development programs worldwide through partnerships that design and implement sustainable engineering projects while creating transformative experiences that enrich global perspectives and create responsible leaders. So that's a lot, but kind of above it is broken down our process. So the communities identify the problems that they see within their communities that they may lack engineering expertise or other or funding to complete or to solve whichever issue that they see. So then they'll seek out help with EWB USA, and then EWB USA assigns those projects to a chapter like the Marquette University chapter. So that's basically what happened with our pedestrian bridge project is the community, identified their need and then came to EWB USA that we got the project. So then from there, our chapter assesses the project, kind of figures out what the best solution is. Once we figure that out, we design it and we fund, not all of it usually, but quite a bit of it. And then when the design is complete, the chapter usually travels to the community to implement the project. Obviously, in COVID times, we can't do that as much as we'd like. So we've been transitioning to remote implementation, but the idea is still that we see it all the way through the construction of the project. And then this is where the kind of sustainability to the engineering projects come in. We then go to the communities after the project has been completely constructed and we monitor how it's doing to ensure that it actually solved the issue, the problem that was present in the community. And then also, if it didn't, or we can see if there's either more we can do or ways to improve projects in the future. And then there at the end, hopefully by the end of it, everyone is happy with the result of the project.
Right, and that's like, as Claire's kind of suggesting, this is like a multi-year program in terms of the adoption of the project, the design, the implementation, and then that monitoring. And actually our project, from the beginning now, obviously there's been delays with COVID. It's been about 2 years since we began our project adoption.
Yeah, so we assessed in the summer of 2019.
Here's just a little photo of in the background for a second of us on our assessment trip on a different project. This is actually a school project that was implemented 2 summers ago now. It's just a photo of the club, but I think if I click this. The last one. So we've partnered with the Hoyaba Guatemala office, which is in the Quiche region of Guatemala. And we generally design bridges as a chapter. Over the last probably 10 years or so, a lot of our projects have been bridges. We've had a few different projects, including a water chlorination system and that school. You just see the picture in the background. And essentially, like Claire just said in the last slide, we go from assessment to the construction and then the monitoring. And we travel to implement, although obviously given COVID, we didn't really get to do that with our project, and we'll get into that. And so we also volunteer throughout Milwaukee as a chapter. So our chapter doesn't just function in the sense of doing these projects. We also do, volunteering with Habitat for Humanity and things like that. And we have some more like educational functions within the chapter to spread awareness of just the infrastructure situations in the communities we work in. And we do the fundraising for our projects, as well as applying for grants and other forms of acquiring money to fund these projects. Yeah, and then of course, this kind of an encompassing piece of the chapter is that students in the chapter are allowed to use skills that they have acquired in school, as well as things that they learn outside of their classes through the club. So it's kind of an all-around experience for the community as well as the students in the chapter.
Okay, so getting into our project specifically. So like I said, our project was the Praje Las Guacamayas pedestrian bridge. So our community partners for this project is the community of Las Guacamayas, which is a pretty small community made up of approximately 200 people nearby Hoyaba. So Hoyaba is like the municipality, like the larger city nearby that we work with, and then Las Guacamayas is just outside there. And so the community is geographically divided by the Motagua River, which is actually the longest river in Guatemala. So you can kind of see in the background picture that we have here, it's a pretty big river. This is probably after rain events. You can see the water's moving pretty well. And so currently they do have a bridge in place that they constructed 8 years ago without the help of an engineer. But that crossing is pretty unsafe as it is. So the pictures that we have there show the current bridge crossing. And if you can see kind of in this picture over here, the cables are all like unwound. There's separate cables. The decking is not very safe. So overall, it's an unsafe crossing. When we were there on the assessment trip, we crossed it several times, and it's not fun. You can only hold one person at a time. So yeah, that's essentially, they realized that they needed a safer crossing for their community, and that's when they came to us, or to EWB USA. So the bridge uses are generally for the community to either transport goods across the river or to get children to a nearby school. So it's used daily. And like Claire said, very unsafe. It's kind of hard to tell by this photo, but the railings actually are below your waist, which makes it pretty daunting to cross for the existing bridge. It's about 221 feet long. And all those, like the lack of funds they had for the bridge led to a lot of the improper materials used. And you can kind of see the shape that the bridge is in even closer here in this photo. And so our task again is to build a bridge that kind of gets rid of all of these issues that are mainly issues to safety. Okay, so the scope of our project is to replace the existing bridge with a cable suspended pedestrian bridge that the community will feel safe crossing. The proposed bridge is approximately 60 meters long, and it will be designed to be, or it has been designed to be sturdy enough so that they can bring carts filled with goods across, and multiple people will be able to cross at once while still feeling safe. So yeah, basically just addressing all of those issues that exist with the current bridge, so that the new bridge will just be a better for the community.
So for the design process, again, as we kind of mentioned earlier, we adopted this project in early 2019. And we actually went on our assessment trip in the summer of 2019. And on that trip, we gathered all the necessary data, whether that was geotechnical data, cross-section data, and we'll show you some of the cross-sections that we developed based off of the data we took in country. We estimated that the cost for the project is going to be around $29,000. That includes labor now with because of the COVID delays and us not being able to be in country for part of the labor. There's a bit more cost there. The duration is around 37 days, and that again is kind of around the availability of some of the in-country engineers that work with the office. And then we're currently planning a remote implementation. Hopefully within the next month or so is when they're gonna break ground. So we're pretty excited to hear back from them. We actually just sent down our first installment of money for the project. Mm-hmm. And so as you can see this timeline, there's our July assessment trip. We did the alternatives analysis here at Marquette with our project team. This is all pre-COVID, so we were able to work with our in-person project team of around 35 students. And that was a great experience, and we got to do that for that whole year, 2019-2020 school year. The implementation plan was completed at the end of the 2020 school year, and then the implementation trip was canceled, obviously due to COVID, and kind of since then, this project really slowed down in terms of the project timeline, because there was a long period of time where we were waiting to get approval for our design. And then obviously present, we're now getting ready to finally implement, since we were finally approved in December of just this last year.
Okay, so getting into the bridge design itself. So our chapter actually uses the general design specifications from another nonprofit organization called Bridges to Prosperity, and that organization focuses just on building bridges in communities that need them. So they've basically come up with a really great resource on how to design these types of bridges. So we designed the cable suspended pedestrian bridge, and you can kind of see what that type of bridge looks like. So our bridge was in soil conditions. So we have a gravity anchor, which is the type of abutment that you can see on the left of the image here. So the general kind of important aspects of a bridge is the abutment, which includes the tower and foundation, the gravity anchor beam, and this ramp, which you kind of there we go. And then this ramp, which you can obviously walk up to get to the bridge itself. And then there's the bridge walkway over the span itself, which will have, the handrail cable and walkway decking. And then another important aspect of it is the freeboard, which you can see here, which is the distance from the lowest part of the walkway to the high water line, which is important to design for so that the water never reaches the bridge itself, which would just be bad. It could damage the bridge and whatnot. Yeah, but that's basically an overview of what the bridge looks like. Okay, and then here's a close-up zoom in on the abutment, which is important for a lot of our structural calculations. We have to kind of design the dimensions of all of these different pieces of the abutment. So basically there's, you've got the foundation, and then tiers on top of the foundation, which affects the height of the walkway itself. And then you've got your approach ramp, which is normally filled with stone or soil and a grout mixture. And then there's the anchor beam, which is the main force that kind of counteracts the forces that are going across the bridge, like the loading on the bridge. And the way that that works is there are cables that are suspended across the walkway that hold up the decking that people actually walk on. And then these cables go over the foundation and tiers and tower, and then they go back and they are connected to this anchor beam, which is literally just a concrete beam that is buried underground. So it acts as like a giant counterweight essentially to the loading that is placed on the bridge. And then another important factor is like the handrail cable and the suspender fencing. So that's really important for the experience of crossing the bridge, so that one actually feels safe with, you know, a high enough handrail cable and like a sturdy decking, so you're not worried about it breaking or anything. And that's actually something that EWB Marquette has implemented in our past bridge projects. We've kind of decided that the standard that's given with the Bridges to Prosperity manual doesn't have a high enough handrail cable. So we normally add about one more layer of block to the tower. So that adds about 20 extra centimeters, so that you've got about 20 centimeter higher handrail cable, which just really makes it feel safer when you're crossing the bridge, because you've got about 20 extra centimeters on either side of you to kind of like keep you safe as you're crossing the bridge. Yeah, that is the general makeup of what one of these bridges looks like.
So for our assessment trip, we briefly mentioned this earlier, we collected all of the technical and non-technical data. So that includes like our cross sections, our soil data, but then also the non-technical data being questions for the community. And essentially all of those questions are based around making sure that our project meets their needs and how they want it to be. So EWB really emphasizes with, not for, and that's kind of we build projects with the community, not for the community, right? So we don't just show up and build something we think is what they need. We work with the community and make sure everything they want this to be is what they get. And they have just as much stake in this project as anyone else, right? They are also part of the labor. They're also part of gathering materials. So this is their project. And then the logistics of construction, that's also huge on the assessment trip. Just figuring out where we're going to have material laydowns, where we're going to store the material overnight, and things like that. Oh, this is a video. Here's some photos of us collecting our data. That one on the left, so this assessment trip, we actually do off to the side of an implementation trip. So as we mentioned earlier in that school implementation trip, me, Claire, Dr. Federle, and one other student actually leave that implementation trip and kind of truck on over to our own new site. And as you see there in that photo on the left, that's another student. His name is Max, who was very helpful on our trip. And he was helping us gather our cross-section data. And in that center photo, you can see a boy named Jose, who is part of the community, who kind of stuck with us the whole time. And he was a lot of fun. We got to meet some of the kids in the community. And then on the right is a photo of us gathering some of our geotechnical data out of a test pit that the community dug for us.
Mm-hmm. Yeah, just to clarify, so these cross sections that we're talking about, so it's topographical data of the river itself. So basically we're finding like the elevations of different points on the river, because that's very important to be able to design the bridge, because we need to know how the elevations on either side of the river are different from each other, like what that difference is. And also, like where the soil profile and slope is. That's all really important parts of the calculations for designing the bridge later. Okay. And then this is, I was personally in charge of copying down all of the data that we gathered on site. So this is a copy of what I wrote down when I was on site. So basically, this is the info that we got along with the soil test pit data. And this is kind of what we had to go off of when we were designing the bridge. So yeah, it's really important on these assessment trips that you get a lot of detailed information, and I didn't want to forget anything, so that's why I kind of drew these little pictures over here so I wouldn't forget how the different cross sections were oriented to each other. I took a lot of notes about different, different kind of geographical elements that are around the cross sections. Like one has a lot of like large rocks just behind it. Some of them had like trees surrounding it that might need to be cut down if we did decide to construct the bridge there. And then this is all the actual data from the survey. So it includes like the distances between all the survey points and then the angle of the slope. So yeah, it's important to copy all this down and then make sure you understand it later. So I understood all this, but I know a lot of times when I was trying to work with our design team later, they had some trouble kind of interpreting what I wrote down. So yeah, it's important to be able to remember the important data and then be able to communicate it to the rest of your design team.
So after our assessment trip, that's when the semester had kind of begun, and we began our alternatives analysis with our project team. And that alternatives analysis pretty much consists of choosing which one of, well, how we kind of approached it was choosing which one of those cross sections of the river we wanted to build our bridge on for different locations. And so for each different alternative, we made a cross section, we evaluated capital costs, maintenance, the constructability at each of those locations, how the community felt about each of those locations, safety, material availability. Material availability and safety are kind of all the same between the different cross sections. It's more so the costs and design and constructability. And then expandability and scalability. So all three, we kind of want to make sure that there could be future growth within the community. This generally applies to different types of projects mainly, as the bridge is probably not going to lead into a direct different type of project. Although we've had in the past a community, El Aguacate, where we built a bridge for children, similar situations, children to get to school. And because of that increased level of students going to school, they actually needed a larger school. And that was the school project that we built a few years ago, was a direct correlation between the bridge we built before that. So that's something to consider.
Okay, and this is our alternatives layout. So this is actually an attachment that we made for our alternatives analysis report that we turned into EWB USA. So yeah, so you can see here that we had a road from the village to the bridge, which was kind of key in our decision making, because that's how we're going to be getting materials to the construction site. And then, so we ended up going with cross section A as our chosen cross section, and that's just because it was the most, it had the highest level of constructability. It was just going to be easiest to construct there. Then as we kind of stay over here, so cross section B was in the middle of a bunch of trees and it was lower elevations. It would be harder to access and get the materials there. Cross section C and D, moving upriver, it was going to be a wider span of the bridge, so there'd have to be more materials to build it. And also the elevation difference was going to be much greater moving upriver, because the elevations on either side of the river got progressively more different the farther upstream that you went.
Something else that kind of is different than other bridge projects we've done in the past. A lot of our bridge projects have more cross sections. It's always better to get more data. Although, as Claire was just describing, unfortunately, due to the terrain, it was very difficult for us to even get some of these cross sections, like cross section B and cross section D, which had such different levels of terrain. And moving even further down or upstream, it just became even worse. And so really, by the time we kind of evaluated these, even in country, we had kind of known that alternative A was likely our best bet of a location.
Okay, and then for the alternatives analysis, we kind of created these cross-section views. So you can kind of see, so basically Yeah, so this is our cross-section A, which is what we ended up constructing the bridge on. So this is just kind of a general view of what all of the elevations were of our cross-section data points. And then we kind of just drew in to scale the tower and tiers to see what the span would be and what their various elevations would be. So this was cross-section A. And then moving to, this was cross-section B. So you can even see on this one, there's a large difference in the elevation on each side. So on this side, we would have had to build 3 tiers to make sure that the height difference between the two wasn't at an acceptable level. And also, I forgot to point out on the previous one, but this would have a span of 73.8 meters, whereas the previous one only had a span of about 62 meters. And then finally, this was cross-section C. So again, a slightly bigger difference in height, and then also a slightly longer span. This one's about 66.4 meters.
So as part of the alternatives assessment, essentially to choose which one of the cross sections we're going to use, we developed a decision matrix, and kind of, we've already mentioned a lot of the pros and cons to each of those 3, but it came out that alternative 1 or cross section A just had the best scores on our decision matrix, and that's what we went on. And so you can kind of see some of the weights we gave, some of the different items, and we were kind of talking about earlier how like something like expandability wasn't going to have a whole lot of weight for this type of project, but then the community input and constructability were going to be bigger things. And so yeah, alternative A just ended up being our primary choice, and that's what we move forward with for the rest of our design. And that after the alternatives analysis was complete, us and the entire project team began going much more in depth on how the bridge was going to be designed with calcs and everything.
Yeah.
So the implementation plan is the next set of paperwork after the alternatives analysis. And that's where we need all those more detailed calculations, the detailed drawings package. So we have to make, all the drawings we've shown you so far are actually directly from the Bridges to Prosperity manual. And so we need to adjust those drawings to, of course, all of our dimensions, do an accurate material quantity takeoff. We did that for each of the alternatives as well, but obviously we need to do that again with a new design. Construction schedule, safety plan, and operations and maintenance manual. Some things like the safety plan and the maintenance manual are kind of generalized things that we use on a lot of our projects. So those aren't too different between the bridge versus like the school project. But obviously with the bridge project, there's certain like height protection limitations in the safety plan that need to be tossed in there and stuff like that. But that also kind of comes out of the Bridges to Prosperity manual, has a list of those concerns. So moving on and getting into our actual design.
So, so for calculations, the 2 big things that we focus on for calculations are structural calculations and our hydraulics calculations. So the structural calculations, we go through the structural analysis of the bridge to ensure that it can withstand all of the loads that we expect to be going across it. So, and in order to do this like structural analysis, we use a program called MathCAD, which is actually a really great program to use. It's great because you can kind of define all of your variables and give them a value, and then plug those variables into equations like lower down in the MathCAD file and see basically what the result is. So that's great for, because for the structural analysis, there are a lot of iterations of, you know, if we're not meeting a certain factor of safety, what happens if we increase the size of the foundation? So instead of, you know, going through and recalculating everything, all we would have to do is change the dimensions that we have defined for the foundation, and then MathCAD will go through and recalculate everything for you, and then you can kind of compare what that changes in all your calculations. And so there are 4 like main kind of checkpoints for factor of safety in the structural analysis, and that's for overturning, sliding, uplift, and bearing pressure. So overturning would be like the abutment and tower itself like overturning due to the moment about it. that one wasn't a huge issue for us for this bridge. It never really was a matter of concern because we always met that factor of safety. Sliding was a matter of concern, so that would be if the loads that are pulling on the abutment, like towards the bridge, were greater than the loads that are kind of pulling backwards. The whole bridge itself would start sliding forward, which obviously we don't want. So that was a big checkpoint that we had to kind of iterate a couple times to find the correct dimensions of the bridge that would actually meet that factor of safety. Uplift is kind of a similar thing. That's the forces pulling up on the anchor of the bridge versus the weight of the anchor that are like kind of pulling it down. So that was another big factor of safety that we had to change the size of the anchor to match. And then bearing pressure is just, that's where kind of the soil test data comes into play. You need to look at the structural integrity of the soil that you're building the bridge on and make sure that it can actually handle the weight of the abutment that you're building. So yeah, there were a lot of iterations to kind of go through and make sure that we met the factor of safety for all of those checkpoints. And then for the hydraulics calculations, the main thing that you need to meet for that is a minimum freeboard of 3 meters. So basically it's supposed to be from the highest the water level will ever get in like 100-year rain event. So a rain event that's only comes about every 100 years, like that's how intense it is. The water level from that needs to still be 3 meters below the lowest point of the bridge. So usually this is done through a hydraulics analysis software. However, like I said earlier in the presentation, the Motagua River is the longest river in Guatemala. So that would have been an extremely complex hydraulics analysis to go through and figure out what the flows to the river are, because there's just so many tributaries and the watershed is so large. So instead we went a different strategy with this hydraulics analysis, and we used community stated water level data and also comparison to water levels from nearby bridges. So there was actually a bridge in place upstream of our construction site that lasted through a hurricane that actually flooded the Motagua. So we kind of took the data from that hurricane, like what the water levels were at that bridge, and used it to complete our hydraulics analysis.
Yeah, and so for the calculations and all of these like different factors of safety, of course we need to meet all of them. And so all the while we're doing these calculations, it's all to minimize cost really at the end of the day, is because we could meet all the factors of safety by making the abutment massive, but obviously that makes it impossible to build and the cost goes way up. And so Claire kind of took the initiative on being the structural calculations like head of our group. And a lot of that was kind of finessing what the different values and different sizes of different pieces of the bridge were going to be, because if you make the anchor bigger in one direction, it might change your sliding, but it might bring down your overturning. And so kind of finessing those values was key in having a design that was going to be economical. And so changes to our standard design. So we've kind of showed you some of the Bridges to Prosperity abutments and what they look like. And so something that kind of came up when we were designing our bridge was that constructability aspect, and mainly that has to do with our excavations. So both sides of our bridge essentially have really rough excavation areas. The one side of our bridge, the north side of the river, has a lot of rocks and boulders in the way. So we, of course, want to minimize excavation there because we're not sure what we're going to run into when we start excavating. And we don't want to have to potentially move the bridge or have a major design change on site. And then the other side has very few rocks. It's in this cornfield actually, but has such a high slope that we would just be excavating so much dirt. And in order to maintain like a safe level of excavation, you can only excavate at a certain angle given the soil conditions. And so we would have had to excavate like all the way up the mountainside. And so we needed to figure out ways to really minimize the excavations, but that meant shrinking our abutments, which meant not meeting our factors of safety. And so that's when we actually reached out to our mentors and sat down and really had some big changes to our design. Some of our mentors had some great ideas when it came to changing the standard design of the manual in order to kind of meet these difficult parameters we were faced with. And so essentially to account for the loss in size of the abutment going backwards, like the length of the abutment, we actually widened the anchors. And the idea of this is, one, the anchors are now larger, so they're bigger, right? And that's just obviously better because bigger is better and there's more force. But then because the anchors are actually wider than the ramp itself, they're actually capturing the soil that's in front of the anchor on either side of the ramp. And we'll kind of explain this a little more when we get into a picture, one of our drawings. But the idea is that it's just capturing more soil. And because it's wider, there's also more soil on top of it that's going to be refilled on top of the anchor, which is adding more weight as well. And so when we factored in all of these different soil weights, we were actually able to meet our factors of safety, even though our bridge is much shorter than a typical Bridges to Prosperity bridge of our span length. And we'll show that in the next slide.
Yeah, so this is our actual official drawing that was approved of one of the abutments. So like Matt was saying, this right here is our anchor. So standard Bridges to Prosperity design would be the anchor is the same width as the abutment. And you can see here that we've extended it. So basically this will be buried underground, as you can see here. So this is the anchor from the side view. So this will be buried underground. So all of this soil that's in front of it will be the soil that's captured, and all of that weight is also going to be resisting the loads on the bridge. And then one more thing that we also did to minimize excavations is we raised the anchor up. So usually an anchor is on par with the bottom of the foundation or even lower. So we raised it up to minimize this depth of excavation, which also kind of messed with our factors of safety and meeting them, which is why we ended up extending the anchor. But yeah, that's what our end result looked like after going through this iterative process of making sure that our structural analysis of the bridge worked.
Right, and something to note as well is our design is actually still conservative. And while this in capturing the soils kind of calculation we did is not something normal in the manual, we still wanted to make sure, our mentors wanted to make sure that our design was conservative enough that, you know, doing something outside of the manual wasn't going to cause a bridge failure in some way or another. And so not only is this capturing the soil directly in front of it, but because of the angle of soil friction, we're actually capturing cones of soil in front of the anchor. So, and we didn't even factor that in necessarily to some of our calculations. So our weight of the soil is actually less than it's actually going to be, meaning our design is still conservative to the point where there shouldn't be any sort of bridge failure. It's over designed. So construction quantity takeoffs and estimates, that we did for the alternatives analysis, but then of course had to do again for this. This is pretty straightforward. We had a whole construction team working on our quantity takeoff. And so we kind of divvied up the work, figuring out the different aggregate versus, you know, rock, cement, sand, all of that, most of which we've had historical data essentially on our different ratios of sand to cement for projects done in Guatemala. And we kind of followed those previous examples of bridges as well as other different projects for when it comes to making concrete. And so, as well as using data that we were given for unit prices. And so you can kind of see in the background just a little bit of what our quantity estimate looks like. And we will also show you the quantity estimate if anyone asks. And yeah, essentially it's pretty straightforward. We did, of course, had to add labor, as we mentioned towards the beginning, because of the remote implementation, and the total cost came out to $29,000. Pre the labor that came out to be $11,000 for the labor. So the bridge would have been a decent amount cheaper had there not been a remote implementation. But this is a good price for the labor, we believe, and we would have also had to pay a certain value in order to even travel to the country for the expenses of us being there as well. So at the end of the day, we didn't really lose any money, which is good.
And then a remote implementation. So the final step is implementing it, which is going to hopefully start soon. So we actually had a pre-construction meeting with the Guatemala EWB office, and we met with like the project manager, the mason that will be on site every day, as well as the engineer that will be going to site periodically to supervise and make sure that things are being built to our design specifications. So we'll be getting daily brief updates from that team. We're going to create kind of a group chat to get those brief daily updates so that they can ask us questions and we can be sure to just stay updated on the progress of the construction. And then certain milestones of the project we've identified will require more in-depth data to make sure that the bridge is being built to match with the drawings, and if it's not, that we can check the calculations and make sure that it will still be safe. So there's 3 major milestones. So that'll be measurements of the excavations to make sure that they're in the right location, they're the right size, that they're square to each other across the river. And then once that's done, they can move forward, and then we'll need to get measurements of the abutment. So make sure, the foundations, the tiers, the length of the ramp is all as designed before the cable pull. So the cable pull is when you literally pull the cables across the river and set them in place and connect them to the anchors. So that's a major part of the bridge. That's like when loading will start to be placed on the bridge. So that's why we need measurements of the abutment before that happens. And then measurements of cable sag. So that's when you set the sag of the cable to make sure that it's the correct, basically that it's in the correct position as designed. So those are the major things that will require the engineer to be on site and give us dimensions and measurements of all of those. And that's all we have. So thank you for listening to us and learning a bit about our project. And if you have any questions, we are happy to answer some.
So we also have, sorry.
Go ahead, Matt.
As for the questions, we have pretty much all of our detailed estimates as well as the calculations and things like that ready. So if any of you have questions regarding that, feel free to ask that.
Dan has said he wants to learn to be an engineer now. He's at that point in his life. So maybe you could talk a little bit about the loading of the bridge. So where did the amount of weight that the bridge would have to support from a live load standpoint, what drives that calculation? And I'll let you answer that, and then I have another one after that.
Okay, yeah, so that's actually something, so that's a design criteria that the Bridges to Prosperity manual actually sets. So the way that they design it is the loading on it is actually way higher than the loading would ever actually be on the bridge. So it's a very conservative design because the way that they design it is a fully loaded bridge. So imagine like the entire bridge is filled up with like carts full of goods or cattle or something. And I used to know this, but I can't remember off the top of my head what that number is, but it's a very high, like per square foot loading number. And yeah, so that comes from the Bridges to Prosperity manual, that design criteria.
Yeah, and just to add to that, it's literally cows, or I always use oxen nose to tail, as if somehow cow number 2 is going to stick his nose up the butt of cow number 1 and do that all the way across 200 feet, which is optimistic about being able to train farm animals in that way.
Yeah.
Next question, it was, what is the effect of wind do to the bridge, and was there any consideration for mitigating that? I'll phrase it that way.
So the effective wind of the bridge, obviously, so these cable suspended bridges can easily be affected by strong winds, and they can actually cause a lot of problems. And so our bridge is pretty long, and so there's actually a lot of area in which the wind can impact our bridge. But we discovered while in country, and this is something that we have data on in the valley, as well as just being there in country, that the wind would never exceed points where there would be a concern to the load on the bridge, as well as the Bridges to Prosperity manual includes a certain value of that load increase where you would need wind guys attached to the side of the bridge and then attached to either side of the river. Luckily, we did not have to design for those because those can be difficult to install and design for. And so we were kind of spared that.
Great. One of the questions, what are you guys doing after graduation?
Well, yeah, so I'm graduating this May, and I actually have a job that I will be beginning sometime in June. It's I'll be working in Chicago. The company's called Hay & Associates, and it's a civil engineering consulting company.
And while I'm a senior and I'm taking senior design this semester, I will be graduating next December because I took a co-op earlier in my time here at Marquette. And this summer I'll be interning with Mortensen Construction here in Milwaukee on a job in Sheboygan, actually. So not really here in Milwaukee, but and then hopefully I'll be looking to get a job with various different general contractors next spring.
Great, thanks. And I'll answer one. So one of the questions is, once built, is there much maintenance needed? And predating these guys, the very first bridge we built under sort of my faculty mentorship, I suppose, we built using a wood called bullador, which was the most dense wood we could find commonly available in Guatemala, and trees it rotted within 18 months, so we had to replace both the deck and the cross beams. Since that bridge, there's a treating facility in Guatemala, so we can now get treated lumber. And literally, when we placed the order for the wood, before we placed that order, there were trees that existed, and those trees stopped existing once we placed the lumber order, and then they treat them in a way like the US would have done 30, 40 years ago. And thus far, we think that deck and those cross beams will last at least 10 years. We don't have enough data to, because it predates you, got maybe 5-6 years ago that so thus far, when we go back and look at those bridges that are 5 years old, they look like they'll last much longer than 10 years. So beyond the deck, beyond the wood, the fencing should last at least 10 years. And then about the only other thing the community has to be concerned with is making sure during significant rain events, the water doesn't wash next to the foundations to where we get concerned about erosion and those kind of things. We do, in normal times, go visit the bridges every year. One, it's fun for me to see the old bridges that we built. And two, it's an obligation that we have as EWB Marquette, and just an obligation in general. So one of the questions asked is there a way to build the bridge in simulation and test the calculations? Have you seen? I haven't seen that, so I'm throwing it to you guys.
Yeah, I don't think that we've we've never really used it like a simulator for any of the different loadings. So but yeah, I guess that's kind of what we do with our structural analysis, is that we say what the loading on the bridge is going to be, and then we kind of send it through all of the structural analysis calculations and equations to see what those factors of safety would be. But yeah, we don't really run simulations with like different types and styles of loadings. We just do the standard loading.
We have created a 3D model of a bridge in the past, I believe.
Yep, that's true.
Yeah, Claire and I did not do that specifically for our project, but I do believe we have a 3D model somewhere, and I think that was probably created in SolidWorks or something like that. I don't think it was meant for testing, but bridge, obviously there is software out there where you can test like suspension bridges and things like that, and you might be able to test cable suspended bridges as well, but yeah, we don't use that.
Yeah, that was a previous bridge that was done as part of senior design. So the senior design professor, who was me at the time, made him make a model as part of it. So truth be told, I think we've answered all the questions.
If there's any final comments, feel free to unmute yourself.
How did you get the initial cables across the river?
So we haven't done that yet since the implementation hasn't happened yet. But we believe that that's something that we'll probably have to work out with the mason and the engineer in country. But we believe that we'll probably end up using the existing bridge as a way to kind of get that across and pull it across. Or set up some sort of like pulley or cable car system.
They've also used lines to get across in the past and then pull the cable across, but obviously these cables are huge and heavy. Federle, Dr. Federle, I believe, also probably has a few more comments on this because he's seen this happen multiple times.
So John, it's three basic ways. Using the existing bridge is one, setting up a cableway system is a second one, and so that's basically use one of the future cables to span the river and then actually transport materials back and forth. I would be stunned if they don't use that method on this bridge. And then one is literally, well, there's four, I suppose. Third one is throw a rope across and then put some folks on the other side pulling as hard as they can. And then the fourth one is literally the Guatemalans, in the absence of this bridge, walk across the river anyways. And so as long as it wasn't a high water time, there'd literally be two 20-year-old Guatemalans that decide they were going to go down and back up and drag the cable with them, or a rope with them, and then drag the cable that way.
That's what I thought.
Yeah, it all depends on who's on site that day and whether they can distract us so that we're not paying attention.
Thanks, everybody. This has been great. I've got to leave, but
You bet. Thanks for coming, John.
Thank you.
I think that about wraps us up unless there's any other comments. Great. Thank you so much for a great presentation, Claire, Matt, and Mark.
Yep. And Claire and Matt, one of the comments I want to share with you is thanks for your presentation. You make me more optimistic about America's infrastructure needs. So no pressure on you guys at all. But no, thanks for doing this, guys. I'll talk to everybody later.
Great,
and again, I'm not driving.
Program.
Yep, absolutely. You guys did great. Talk to everybody later.
Thanks so much. It was a great program.
You.
Of course.
Have a good one.